Hello, good morning, student. How are you? I hope you all are happy and healthy at home. What did we discuss yesterday? Yesterday we discussed about the strength of bases, means basicity. What are the factors affecting strength of bases? And I think we have discussed two applications so far. Now let us move on to the next one. Is a third application. We are talking about all amines are stronger bases than the ammonia. All amines are stronger bases than ammonia. Explain ammonia. And as we know that everybody knows that the structure of ammonia. What is the structure of ammonia? This is the structure of ammonia. NH3, that nitrogen atom containing always lone pair, capable of donating lone pair, and therefore it acts as a basis. Ammonia are bases. And as we know that its pK value of ammonia is found to be, I think, 9.8 something, right? Now all amines, here we are going to consider the general amines, primary amine, secondary amine, and the tertiary amine. Specifically we are going to consider here aliphatic compound. We do not considering here as a aromatic, remember, only the aliphatic you know that, right? Now suppose as a primary amine, we know that one of the hydrogen atom from the ammonia get replaced by R group, and that is the structure of, this is a primary amine, right? 1:0 is known as a primary amine. And this, if you here pK value is something greater than this one, as you know. This is a general one, and that's why we cannot determine or we cannot mention here pK value. But remember, in general the pK values are greater than the ammonia. It may be as a 10 point. Suppose if you take as R is equal to methyl group of the methyl group or ethyl group, you then let us see, here is a methyl group, then pK value is found to be 10.6 something. Now let us see, there is a R2NH. This is a secondary amine, and now third one, as we know that R3N, this is a tertiary amine. So these are the amines. Now if you look at here carefully, what do you see here? There is a R group. We know that R group means alkyl group or ethyl group. They are the electron donating group. If you consider here, this R group is an electron donating group, and therefore it exerts as a plus I inductive effect. But here R2 means, here you can write for clarification RN, here R and this is H. So there are two plus I effects are present, plus I effect, and therefore this one RN, then you can draw R, here is R. All are the electron donating group. They shows or they exerts plus I inductive effect. Remember here they are showing as a plus I inductive effect. Here only R, then NH2, only one R is there, plus I inductive effect. If you go from this side to this side, what is happening? Plus I inductive effect goes on increasing. Plus I effect goes on increasing, and therefore what do you expect? Then the acidity, basicity also goes on increasing. That is the expectation, right? The expected order is this one, expected order of basicity here. Expected order of basicity basicity. What is that? Suppose here is ammonia, NH3. Then let us see here primary amine, then secondary amine, then tertiary amine, right? Tertiary amine is found to be the strongest base. If you show this type of the arrows, then what do you find? This one is the most one, but actual order of basicity, and this basicity, if it is measured in a gaseous form, right, in the gaseous phase or in the gaseous phase, what is gaseous phase, then this expected order of basicity and the what we can call it as the actual order is found to be this one, because the plus I effect increases, the basicity goes on increasing, and therefore there are 3 plus I effect, and due to this reason that tertiary amine is the strongest base. But actual order of basicity, here actual order of basicity is found to be secondary. Here secondary amine is stronger than tertiary than primary than ammonia, NH3. Here secondary amine is found to be strongest one in the aqueous phase, aqueous phase. In the aqueous phase, secondary amine is found to be the strongest one. The reason behind it, now if you observe here actual order of the basicity, secondary amine is the strongest one. How do you explain, how do you justify this? In a gaseous there is no change. If plus I inductive effect increases, the basicity goes on increasing. But in the aqueous phase, means in the water phase, what is happening? Secondary amine is found to be the strongest base among all these things. What could be the reason? And therefore the basicity is basicity not only depend upon the plus I inductive effect, but also depend upon the solvation of the bases. And therefore now let us look at here why secondary amine is the strongest one. That answer we are going to find here. Suppose here, as we know that primary amine R N H is this one. When it is pick up the proton here, what do you get? You are going to get here R N H then H, positive charge over there. There are the 3 positive. This is a primary amine, right? Primary amine get solvated through hydrogen bonding H2O. This OH2 and then again is a OH2. This is solvated by H2O, right, through hydrogen bonding. And then solvation, it is another factor which decided. This is a primary amine, and if you look at in the secondary amine, this is a primary amine. Let us look at here secondary amine structure. So let me draw here properly so that you can see the correct structure of that secondary amine. As we know that secondary amine, here N, 1R is here, and now this is a hydrogen atom, will pick up the proton here, and what do you get? You are going to get conjugate acid RN, here H, and here R. Now this OH2 here also has a OH2, and this is a secondary amine get solvated by the water molecule through hydrogen bonding. It get whatever conjugate base is formed, that conjugate base is well stabilized due to the hydrogen bonding. And in case of the tertiary amine, look at here, tertiary amine has a structure, this one R, again H plus, then this lone pair pick up the proton and you are going to get here R, N, then R, and one H is there, that is OH2. Only one in a tertiary, this conjugate base, the conjugate base formed in the tertiary, there is only one water molecules are involved, and therefore they create the lot of steric interactions are there, and due to this reason the secondary amine, this secondary amine plus I inductive effect as well as plus I inductive effect and the solvated effect, both are oppositely controlled by this, and therefore the resulting secondary amine is found to be stronger than tertiary amine than primary than ammonia. That is the actual order why secondary amine is the strongest one, because that conjugate base formed, that conjugate base is well stabilized due to the solvation through the hydrogen bonding, and therefore this one is a stronger base than the other amines as well as ammonia. So this is a third application. Now move on to the next application. What will be the next application? Let us see here. Fourth one, on the basis of I think on the basis of resonating effect. Whatever we have learned so far, all about the aliphatic basis, or now we are turning or moving toward the next point on the basis of the resonating structure. On the basis of resonating effect, we are going to explain the following molecule, why one of the molecule is a stronger over the another one. That kind of the concept you are going to learn here. Suppose let us consider on the basis of the resonance effect. On the basis of resonance effect, we are going to learn some of the application of the strength of acidity as well as basicity. So that is the common point we are going to learn here, resonating effect. And as we know that resonance effect means what? The redistribution of electron operating in an unsaturated system via pi bond is known as a resonance effect. And that resonance effect, normally resonance effect is divided into two types, or there are two types of the resonance effect. One is called as a plus R inductive plus R effect, and second one is called as a minus R inductive effect. What are the group that shows as a plus R inductive effect? What are the group that shows as a minus R inductive effect? Remember, electron donating group exerts or shows as a plus R inductive effect, whereas minus R inductive effect means electron withdrawing group that exerts the minus I effect, and that, remember, minus R effect, resonance effect, increases the acidity, whereas plus R inductive effect decreases the acidity. That you remember. And therefore let us see the first application on the basis of resonance effect. The first application here we are going to learn what is that. Phenol is acidic in nature than cyclohexane, or phenol are acidic in nature. Explain. Phenol is acidic in nature. Explain. Phenol is acidic in nature. Explain. So that is one of the application which is based on the resonance effect, and resonance effect is found to be in a conjugated pi bonds, or that conjugation must be carbon-carbon double bond. Suppose as this type of the conjugation, carbon-carbon double bond, then and then there is a possibility of resonance form, or if this carbon-carbon double bond, then there will be a empty p orbital, or suppose carbon-carbon double bond and there may be as a nitrogen which is in a lone pair like this, then and then resonance effect is possible. Suppose we have this one, radicals are there, then and then there is a possibility of resonating forms are there. So that type of the systems are there, they can show as a resonance. So now phenol is acidic in nature. Most of the time, true or false in multiple choice question also there, phenol is acidic in nature, and everybody, I think 95% of the student might be knowing the structure of phenol, right? So do you know the structure of phenol? Yes, you are knowing the structure of phenol. Everybody knows that this is a structure of phenol. OH, one of the hydrogen atom get replaced by the OH group. This is the structure of phenol, right? So phenol, this is the structure of phenol, and the phenol are acidic in nature. Now this is a OH. After the dissociation, what do you get? Minus, it produces as a H plus, and whatever we are going to get here, this is O minus charge over. After losing the proton over here, it form as a negative charge, and when negative charge present on this, that type of the species is known as a phenoxide ion. Understood this one? This is a phenoxide ion. Negative charge present on it, and that is called as a phenoxide ion. And when this happen, after the phenoxide ion, what is this? This is nothing but as a conjugate base, and as the beginning, the strength of acidity factor we remember. If you recall, what do you see there? The one of the factor, the stability of conjugate base. Look at, this is the nothing but as a conjugate base, and that conjugate base in this case are well stabilized due to the resonance. Look at, and as we know that how to draw the resonating structure, we already know while studying as a resonating structure. I think 2 examples we have already seen there. Let us see again, follow all the rules. The resonating structure, or it is called as a canonical form or canonical structure, or it is also known as a mesomeric effect. And in first rule, there must be conjugation, and then two structure are interconvertible, and these two canonical form or the resonating form is shown by double-headed arrow. Remember, this is a double-headed arrow. Most of the student, this is a equilibrium arrow, this is a double-headed arrow, and double-headed arrow means this is a resonating structure. And how to draw that resonating structure? This negative charge comes down here, and this carbon-carbon double bond, look at carefully. If you pay the attention from the beginning, how to draw the resonating structure, you never forget in your whole life how to draw that resonating. But clearly see here how I am showing as an arrow. When this negative charge forming as a double bond with this oxygen and this carbon, now this double bond concentrate the electron density at this corner point. Exactly show the how the arrow is pointing there, and you are going to get the structure here. This one, negative charge over there forming as a double bond. Look at this double bond and this double bond, they are as it is intact. Now this negative charge, just like as a water flows from higher level to as a lower level, similarly this negative charge coming down forming as a double bond over there, and this double bond concentrate the electron density at this corner point, and you are going to get the structure over here. This one, look at again carefully, this double bond and this double bond as it is. What are the changes I made there? I made the changes here, double bond, then this double bond concentrate the electron density at this corner point or at this king ki king. And now what is going to happen? Don't show arrow reverse manner or counterclockwise. Once you started from the clockwise manner, you should follow that order only. Remember that one. Now this negative charge again forming as a double bond exactly the middle of these two carbon atom, and this double bond concentrate the electron density at this corner point, and therefore you are going to get the next structure will be what are the changes I made? Negative charge over there, double bond here, this double bond as it is, and this double bond also as it is. Now let us see the another one. This negative charge forming as a double bond over here, and this one of the double bond concentrate the electron density on that oxygen atom, so that finally you are going to get the structure over here, double bond here, O minus charge, this double bond and this double bond, they are as it is. If you see the structure carefully here, this you can call it as a structure number 1, structure number 2, structure number 3, structure number 4 and structure number 5. If you observe the structure number 1st and the 5th one, what do you see? Both the structure are identical, but in a first the double bond on the right hand side, in a 5th one double bond is on the left hand side. That's the changes only. Now observe this structure 2nd, 3rd and 4th carefully. What do you see over here? Here the negative charge on that on ortho position, these two position are called as ortho position, exactly opposite that oxygen is a para position. There are the negative charge. When you are going to learn, you might be knowing as a sum of the aromatic compound, they undergoes as a electrophilic substitution. If the substituted aromatic compounds are there, if they is having as a electron donating group, then and then they gives as a ortho and para product. Why they gives a ortho and para product? If you know the resonating structure concept clearly, then and then you can able to predict the product. Look at here at ortho position, what do you see? Positive charge. And whenever you are you already studied that nitration, sulfonation, halogenation, Friedel-Crafts alkylation, Friedel-Crafts acylation, and there is a electrophile, means NO2 group means electrophile. Look at ortho position, there is a negative and here is a positive, and that's why we are getting as a nitro. Here para also there, and among para and ortho, which one is a major? Para is always major and ortho is a minor one. That we will see while studying as aromatic compound. But here just remember why they are at ortho and para. That is the reason involved here. Those are knowing the resonating structure, and that's why when this delocalization of that negative charge operating via pi bond, and again it comes on its original position, it took the long time to come on its, and then it will pick up again as a proton. So that's why phenol is acidic in nature, because the phenoxide ion is well stabilized due to the resonance effect. Is well stabilized due to resonance effect, and that's why the phenols are acidic in nature. That is the answer of this question. Now moving toward another one more point you remember here. If you look at here, okay, let it be here. Now let us move on to the second application. Here see the second application. Now in the second application here, phenol are acidic in nature. Phenol is acidic in nature, while alcohols are neutral in nature, while alcohols are neutral in nature, explain. How do you explain this one? Just now we already learned that phenol is acidic in nature while alcohols are the neutral in nature, is both containing as a hydroxyl group, right, OH. And phenol structure we know that just now we have learned the structure of phenol is this one, OH. This is a structure of phenol. Why phenol is acidic in nature? In the previous application we have already draw the resonating structure. This after the dissociation whatever conjugate base is formed, and that conjugate base is well stabilized due to the resonance, and due to this reason phenol are acidic in nature. Whereas alcohol, let us take down the example of alcohol here. Let me draw here OH. What I drawn the structure of, I have taken the structure of cyclohexylamine. This one is a cyclohexyl alcohol, cyclohexyl alcohol, right? And this cyclohexyl alcohol is a neutral in nature. Why this so? Our alcohols are the neutral in nature. What is the reason? Here just remember the OH attached to this carbon atom. Look at here, this carbon atom, OH attached to this carbon atom. This carbon atom shows what type of the hybridization it shows. And as far as the organic chemistry is concerned, there are three kinds of carbon atoms are present. One is a sp3 hybridized, second one is sp2, third one is a sp hybridized carbon atoms are. Now if you look at this OH attached to this carbon atom is a sp2 because there is a carbon-carbon double bond, and therefore it shows as a sp2 hybridization, and sp2 hybridization exerts minus I inductive effect. And now if you look at OH in a cyclohexylamine, this is a aromatic compound, this is a non-aromatic compound because there is no double bond, saturated compound this one. And if you look at this carbon atom over here, what do you observe here or what do you see here? This carbon atom is a sp3 hybridized, and sp3 hybridized, what type of the inductive effect they shows? They shows as a minus I inductive effect, and minus I inductive, here is a plus I inductive effect. It shows as a plus I inductive effect, and therefore first one you draw the resonating structure of phenoxide ion. Just now we have already seen this one, phenoxide ion. After the dissociation minus H plus, we are going to get minus charge over there, and this is well stabilized due to the resonance. You are going to get here minus charge, double bond O, this double bond and this double bond, they are remains as it is. Then you can draw the resonating double bond comes here, then negative charge over there. You are going to get another structure, negative charge over there, double bond, this double bond as it is, then double bond O, then negative charge goes there. Then we are going to get another structure, this one, negative charge, double bond O, this forming double bond here, this double bond, and next one, this one, what is that? Negative charge goes there, and O minus, then double bond and this double bond. Look at the structure number first, second, third, fourth and fifth. There is a one hybrid resonance also there, but let us see in the first case. First reason, you have to draw the resonating structure of the phenoxide ion. Phenoxide ions are well stabilized due to the resonance. And second thing, look at here, OH attached to this carbon atom, that shows as a sp2 hybridization, and that exerts minus I inductive effect, and therefore it is acidic in nature. Whereas in alcohol, cyclohexyl alcohol, here we have taken this carbon atom shows sp3 hybridization, and that exerts as a plus I inductive effect, and therefore alcohols are neutral in nature, whereas phenols are acidic in nature. So in this way we have seen the two application. Third and nitrophenols are more acidic than the simple phenol that we will see in the next lecture. Let us stop today here. Thank you. Have a nice day.